Hello, let us begin with an introduction to energy. So the AKS we're going to be looking at with this unit is going to be number 14 and number 15. 14 states, explain and apply the law of conservation of energy. And then number 15, relate the effects of thermal energy to kinetic molecular theory. So today what we're going to focus on is just the first AKS. We'll save this for future videos. To get started, make sure that you're paying attention, taking notes, and you're going to be asked to summarize at the very end of the video. So make sure that you have some good notes to use for that. And please be following along in the interactive notes that you will find on eClass. So the first goal that we need to kind of accomplish here is understanding the law of conservation of energy. So what I will say is this. It is very similar to the law of conservation of mass. We know that matter can never be created, nor can it be destroyed. That is the whole reason why we have to balance equations, because we cannot create atoms or destroy them. We have to find a place for them to go. The same thing is true of energy. The law of conservation of energy states that you cannot create or destroy energy. However, bear in mind that energy can, and often does, change forms from one type to another. So we have a lot of different types of energy. We have kinetic energy, which is the energy of movement. Electrical energy, which is basically generated by electrons. Many of you have electronic devices that are operated by electricity. Now, electrical energy is going to be either kinetic or potential, or sometimes a combination of both. We have thermal energy, which kind of relates to heat and temperature. We have sound energy, which is the energy from vibrating matter. So if there's a musical instrument you know how to play, no matter what instrument it is, in some way it's going to vibrate to make that sound. Potential energy, which is the energy, basically this energy of position. If I were to hold an object high up in the sky and release it, when I'm holding it, it has potential energy. When I let it go and it begins to move, that potential energy becomes kinetic. Then we have mechanical energy, which is the combination of potential and kinetic. Chemical energy, which is a type of potential energy, and we can use chemicals in a chemical reaction to basically form another kind of energy from that, and we'll talk a lot more about that later on. And we have nuclear energy, which we kind of discussed a little bit when we were talking about atoms. So nuclear energy is the energy we can get from the nucleus of an atom, and these atoms can either go through fission or fusion. Fusing is when they come together, and fission is when they break apart, but both of these can actually produce energy, although we use one more than the other. We'll talk more about that very soon. So, I want to stop right here, and I want you to pause the video, and I want you to think back about what I just said, and I want you to brainstorm a list of all the types of energy that you can remember that I just said, or I just talked about. Take a moment to do that now. Okay, hopefully you can remember a lot. Let's kind of go back. You can look at the list again. It's right here. Kinetic, electrical, thermal, sound, potential, mechanical, chemical, and nuclear. Now the three we're going to talk about the most are going to be kinetic, potential, and mechanical. And this is actually pretty easy because mechanical is just a combination of potential and kinetic. So basically if you add potential to kinetic, you get mechanical. So when we want to calculate energy, we have to use a formula. And every type of energy has its own formula that it's going to use. One thing that's universal is that energy is always, and it does not matter what type it is, but energy is always going to be measured in joules. And that is shown with a capital J. So you could say the amount of, let's say I have this ball and I wanted to throw it. I could say that it has 25 joules of energy when I throw it. So we measure energy of all types in joules. So, question, going back to what I just said, what unit of measure do we measure energy in? Now this is kind of new because we haven't used joules before. Like when you were in elementary school and even kindergarten, I think you guys were beginning to use centimeters and kilograms and grams and things like that. A rudimentary exposure to the metric system, but using joules is new to you. Long ago, joules used to be referred to as Newton meters. So it was 1 Newton of force accelerated 1 meter, but now we call them joules. So the first formula, and probably the easiest, although there's a little bit of a challenge to it, and I'll talk about it in just a second, but what we have going on is gravitational potential energy. And gravitational potential energy is when I have, let's say I have this object. What I would do is I would multiply its weight times its height. And you can see that, well, it's a ping pong ball, so it has a very low weight, very small weight. I would say you're looking at probably 0.002 newtons. And then I multiply it by its height, which is just over a meter. So if I drop it, here's the idea. The energy that it had, because of how high it was up, that energy was converted into kinetic energy when it fell. So to find the potential energy, or what we call gravitational potential energy, is going to be weight times height. Okay, so weight times height. Now the problem is that we don't use weight very frequently. Most of the stuff we've done, we've used mass. Mass is different from weight. So make sure you understand this. Mass is definitely not the same as weight. Essentially, we measure mass in kilograms. We use newtons for weight. So these are completely different units of measure. Also, remember this. Kilograms are going to be describing a physical property. So when we talk about mass, we are basically identifying that as a physical property of matter, whereas newtons, well, this is describing the amount of force that is present. Okay, so entirely different things. However, we use mass to get weight. Another way we can state this formula, so we have GPE, or gravitational potential energy, is weight in newtons times the height in meters. So weight, height. Another formula we could use is mass times 9.8 times height. The reason this works is because mass times 9.8 is the same thing as weight. So weight is going to be, weight is equal to the mass times 9.8 meters per second squared. And this number is not just some number I made up. This number is actually the force of gravity on Earth. So gravity will accelerate objects at 9.8 meters per second squared. Now we're going to simplify this, and what we're going to say is mass times 10 times height. So yes, we're going to round this number up to 10 for many of our operations, because we don't have to be very precise. We just want to have a general overview of what the number is. That being said, when we write down our answer, we're not going to use the equal sign, but we're going to use the approximation sign, looking like this, to illustrate how much we have for our measurements. So let's move forward. So again, we're going to look at an example. Let me erase this real quick. So in my example, and just kind of going back to what we said before, GPE equals weight times height, which is weight in newtons times height in meters, or mass times 9.8 times height. Again, the mass needs to be in kilograms, the height needs to be in meters, and I'm okay with you rounding this to 10. So let's look at our question. A rock with a mass of 2 kilograms is at a height of 8 meters. How much GPE does it have? Go ahead and pause the video and take a moment to solve that. We'll come back and see if your answer was correct or incorrect. All right, let's look at what we have here. So we have, let's write down a formula first. GPE equals weight times height. We have a mass, but we don't have our weight. So we need to find our weight. So we're going to say that this is the same thing as being equal to 2 kilograms times 10, and then that is going to be multiplied by the height in meters. Now, one thing that you want to be aware of is making sure that you don't have to convert here. You want to double check, make sure that you have kilograms before you multiply by 10. Make sure you have meters before you put that into the formula, because sometimes this number could be in centimeters. Sometimes it might even be in kilometers, and in those cases you would have to convert. So here I have 2 times 10, which is 20. 20 times 8, which is 160 joules of energy. So again, I have the 2 kilograms times 10, because this is the force of gravity, and these two numbers multiply together, that's going to be my weight, okay? And then I have my height of 8 meters, and that's how I got the answer to this question. Okay. Now, one thing I want to kind of go back to is when I drop the object on the ground. So if you look at that, what we can do is we can say we have an object, and it's going to have a certain amount of potential energy. When I release it, it's going to fall, and the potential energy it has, the amount of joules it has, that's going to stay the same. It's not going to change. If I start out with, let's say, 160 joules like I had on the board just now, so if I had 160 joules, when I drop it, it's still going to have 160 joules. But it's going to have a different kind of energy. Its potential energy is going to become kinetic energy as it falls. So one thing we need to be doing here, though, is we have to be aware of something called friction. You see, when I release this, what's going to happen is there's air particles that are going to be touching the object as it begins to fall. And each of those air particles is going to provide some resistance, or it's going to try to slow down or affect the movement in some way. Because of that, I need to subtract a little bit from the amount of energy that it has as it falls. So, not looking into precise measurements, we could say that it would have about maybe 157 joules of energy as it falls, maybe subtract a few joules here or there. But friction is something that's going to always impact energy, especially kinetic energy. Not so much potential energy, because potential energy is really just energy something has because of its position. But when it begins to move, that's when friction is going to come into play. So what we have here, it says when, if we had that rock in the previous scenario in our question, right here, a rock with a mass of 2 kilograms is at a height of 8 meters, how much GPE does it have? That rock, okay, essentially when we drop it, it's going to turn its potential energy into kinetic. And we call that an energy transfer, because the energy is moving from one type to another type. The overall amount of energy is still going to be the same because of the law of conservation of energy. So, looking at friction again, we just mentioned this, but there's two situations in which we're going to have friction. First of all, you're going to have friction occur when there's two objects that are in contact and at least one is moving. So if the ball were falling, the air will be touching it. Air particles are objects, and so the ball is moving, and so that would generate friction. But also we have friction when energy changes from one type to another. So anytime we have any kind of energy transformation from one type to another, or objects are touching and one's moving, we have friction. And what friction does is it basically takes energy and it takes sum away that you're, so let's say you had 160, right? So here's 160, and we ended up with 157. So let's say this was our potential energy, and then this became our kinetic energy. Well, you have to ask yourself, what happened to the other 3 joules of energy? And the answer is, those 3 joules of energy were lost due to friction. But they don't just go away. They actually become thermal energy. So friction actually makes things get warmer because it's turning other kinds of energy into thermal energy. And that's what it does. That's how friction affects energy. Now we need to look at kinetic energy, and I'll say before we get started that kinetic energy is a lot more complex than gravitational potential energy. And that is because if you look at the formula, you can see that in this formula it says Ke is equal to 1/2 mass velocity squared. The one thing I want to say here about this is that there are common mistakes that students make when they are trying to solve problems or equations that involve the kinetic energy formula. And I want to talk about what they are, but let's look what we're multiplying here. Kinetic energy is 1/2, or you could call this 0.5, times the mass. And that mass needs to be measured in kilograms. And then it has the speed, or velocity squared. The unit for velocity for us is going to be meters per second. And so we write that as m/s, meters per second. Our mass, again, is going to need to be in kilograms. Okay? So when you're multiplying these things, these variables or these quantities together to get kinetic energy, you're basically multiplying 4 things together. You're going to multiply 0.5, or 1/2, times the mass, times velocity, but remember velocity is squared, so we mentioned that a second time. So you have mass, 0.5, velocity, velocity, and all of those are getting multiplied at the same time. So, looking at the common mistakes that students can make when trying to solve these problems. First of all, the most common mistake is not remembering to square velocity. If you look here, you can see that in our formula, the velocity is actually squared. So when you're solving this, you need to make sure that you square the velocity. That means multiplying it a second time. So what we have here, what this really represents is 1/2 mass, velocity, velocity. That's the first mistake. The second one that I have found to be very common is students not multiplying by 1/2. So remember that you have a 0.5 here, you also have to multiply everything by. So you're really multiplying together 4 things when you use or apply the kinetic energy formula. Something else that's important to note is that the units have to be precise. Like you have to have mass in kilograms. If it's not in kilograms, convert it to kilograms. Velocity has to be in meters per second. If it is not, you have to convert it to meters per second. So if you have a different time unit or a different length that's being used instead of meters for that part of the problem or that part of the unit, you need to convert that. So let's try to apply this real quick and let's see if we can get this correct. It says a car is traveling at a speed of 3 meters per second. It has a mass of 1,000 kilograms. What is its kinetic energy? Now, you know, these numbers may or may not be accurate or realistic, but that's not important for our purposes. We're just trying to get some familiarization down with how to apply this formula. So let's go ahead and let's start. What I like to do to begin is like to write the formula down. So I'll say Ke equals 1/2 mass velocity squared. Now I can look at what I have in my statement here and I can kind of move that over into the formula. So again, writing down kinetic energy, 1/2 is the same thing as 0.5, okay? So it's 0.5 times its mass, which is 1,000 kilograms, times its velocity, which is 3, times its velocity again, which is 3. So remember that you are multiplying together 4 things to get your answer. So let's go ahead and let's just look at it. I know that 3 times 3 is 9, and that 9 times 1,000 is 9,000. 9,000 times 0.5 is going to be 4,500. So my answer is 4,500 joules, okay? Now before I did that, I should have checked to make sure that my units were in the SI units. I need to make sure I have kilograms, because that's what my formula requires. And I need to make sure that I have meters per second, because my formula requires me to have the right unit for velocity as well. So, the last one we want to touch on today is mechanical energy. And I'll say that mechanical energy is really the easiest one of all to calculate. Understanding it can be a little bit challenging, but not very challenging. Okay, so here's a general idea. And this illustration does a great job of showing what we're talking about. If someone were to raise a hammer up, when they raise the hammer up and they prepare to lower it, they are basically having potential energy, stored energy, or energy because of the position of the hammer. Same scenario with a basketball. If you're getting ready to shoot a basket, and you pull the ball back and getting ready to shoot, or to take a shot, you have potential energy because you're about to release it, and it's energy that it has because of its position. When the hammer is actually swung and it's moving, it has kinetic energy. So this energy becomes kinetic. Now, the overall combination of these two, if you add these two together, that's what mechanical energy is. Another scenario. Here we have the bowman, and he pulls the string back on the bow with the arrow in. When he releases that string, the arrow flies forward. So basically, when he pulls back, he has what we call potential energy. This type of potential energy is actually called elastic potential energy because it deals with the springs and things like that. But he pulls the string back. Basically, he's storing energy in that arrow. And when it's released, that potential energy becomes kinetic. If you want it to fly faster, you can pull back further so that you get more energy stored into the arrow. When it's released, it becomes kinetic. Again, combining these together, adding them is going to give us mechanical energy. Another example, here's a ride at Disney World, the Seven Dwarfs Mine Train. Roller coasters operate on the principle of mechanical energy. When the coaster goes up a steep hill, it has potential. When it comes back down the hill, that potential energy becomes kinetic. And I'm sure that you realize the higher up it goes, the more potential it has. And so when it drops, it's going to move much faster. So we look at that in a diagram. Here we have the cart, or the coaster, and we have two bar graphs. We have one that shows kinetic energy and one that shows potential energy. And so what you can see here is